Hello, everyone. Thank you for the introduction, and also thank you very much for the invitation to this meeting. I would like just to say that I wish that the organizers had informed us that the food is going to be so good, and there's so much of it, then I actually would have packed anti-acids with me, and my week would be easier. But okay, okay, thank you. So with that, I would like to begin the talk. So in particular, I would just first like to acknowledge my collaborators on this project. So the very first part of the talk is done with a collaboration with Christoph Koller, who has now moved to Alto to Pivy group, and with Votien Fong, who is in my group as a postdoctoral fellow. Okay, and our experimental support plus motivation is that from group of Matt Yankovic and Joshua Island, and the two projects that I will be discussing are available on the archive. Okay. So let me begin with the motivation. So this whole project began with an email from Matt, who has asked me, Cyprian, in a large set of our data, what actually I see is there are these appearance of regions that are controlled only by a single gate voltage, despite the system being in a dual gate geometry. So actually what he means by this is that normally when you see the experimental data, very often you just see an ND cut, and it's actually not showing you where are the gates voltages. But if you do show the edges of the two gates, then Matt has noticed that in a large set of his data as well as other people's data, there are these regions that appear to follow a single gate. So actually what that means is that for a large range of gate values, in this particular this gate, the phase boundary seems to be independent of that gate. Okay, and this is not just limited to the MU-RS systems, but it's actually also an effect which is present in rhombohedral systems, as I am also going to show you. So in particular, for the very first part of the talk, I am going to be talking about twisted double by layer graphene as an ideal system to look at it. So this is AB graphene twist AB. Okay, this is taken from the existing publication from Mass Group, and the two generic features that I am looking at is A, that there's a region of symmetry breaking, which is a transition to a half metal, that's this thing here, and it seems to be controlled by these two boundaries that mirror one of the gates. And then we also have a second feature, this X here, this very faint higher resistive feature that is also following a single gate. So this is just for me trying to emphasize is that as a theorist, I actually tend to look at such maps and I either see deep blue or deep red features, right? But there's a lot of other colors in between on the color map, and they are not just there to sit idle, they can actually shed some more information. And just to point it out, that if you look at the family of the rhombohedral graphene systems, and if you're looking at n equals to 5, perhaps you are not yet seeing any lines, and neither did I at the beginning, but as I hope that at the end of the talk you will begin seeing lines everywhere, okay? And in particular, if I keep increasing the number of layers, so this is just some sets of data that I found online, and I am sorry if I have missed anyone. So for example, for n equals to 6, you are beginning to see these boundaries here that follow one gate, and those boundaries over here. Similarly for n8, you are seeing such features, and ultimately you can also go to an infinity limit where you are also seeing such features that seem to follow symmetric on a single gate. Okay, so to me, when I see an effect like this, which is fairly robust amongst many devices, you don't need to particularly cool your device. So this is telling me that most likely the effect is electrostatic in origin, and indeed that is what is the case. But this actually lets me formulate better what is the theoretical motivation for the talk. Okay, so one thing is to ask is what is the layer dependent Coulomb interactions in the systems. So let me make it sharper. So typically when you look at the literature in this field, if it's a dual gated geometry, the standard form of the Coulomb interaction that is being used is this form of a tangent with a QD. So this is particularly a true form of the Cyprian interaction only if you have a single layer or layer which is very thin as compared to the gate distances. And just a historical fun fact that I think the very first place where this form of interaction was used was in Oscar's paper, and I don't know of a version of this being used before, just so that if people were curious. Now if I add more layers, as I do in these rhombohedral end systems, for example, and the thickness of the dielectrics now is not 100 nanometer or more, it's actually 30 nanometers, then perhaps I should be thinking that the Coulomb interaction between, let's say, charge here and charge here is going to be layer dependent. Okay, and this links us to the second question. Is actually how do I account for the displacement field, meaning unequal charges on the top and bottom gate in this geometry consistently. So the common approach in theory is that if I model my system as n different layers, on each of the layers I would put a layer dependent potential, and the common way how this is modeled, which is valid in a certain limits, is that the difference between consecutive layers is fixed. So consequently that means that the layer potential is uniformly changed as you go from bottom to the top of the sample, which is an assumption that doesn't need to hold, and in fact it does not. Okay, so the way how I can capture this faithfully is to analyze the microscopic form of the Hamiltonian that I have in the system. So firstly, what I would like to emphasize is that if you look at the standard form of any of those continuum model Hamiltonians, they locally have an AB stacking form, which means that at Dirac point, or a point where k is equal to 0, right? If I put 0 along this direction, 0 along this direction, I have a perfect eigenstate which is localized on a particular surface layer. Okay, and as I move away from that point, of course, this perfect layer polarization will disappear, but nonetheless, there is some form of it, and that's indeed what we see in rhombohedral systems too. Okay, and now, in order to analyze what actually this single particle Hamiltonian gives you, is that I will allow for this layer dependent potential U1 and so on, but I will for now not connect it to the displacement field. And if I do it, what I find that for a fixed constant layer potential difference, the generic plot of the density of states looks as follows. There's a high density of states feature, okay, and that high density of states features, it actually is connected to the locally flat part of the band where I have a perfectly layer polarized state. Okay, And in this particular calculation, what I am taking is I am choosing an electrostatic gauge where I set U1, which is the electrostatic potential on the bottom layer, to be 0. But that's a choice that I can make. And I am making this choice because what I would like to use as a theoretical tool is that I am tracking the location of the surface state as a function of back gate and top gate, and I am taking it as the appearing just next to high density of states region. So if I can form description of what happens to the surface state, I can then tell you what should happen in the transport map, as I can connect the high density of states to those features. Okay. So how do I add interactions to it? How do I add electrostatics? So at the formal level, if I would like to describe what's the form of the Coulomb interaction in this multi-layer geometry when I account for the distance between the layers, this is a fun electrostatics problem that actually you could solve with the method of image charges. So if you're teaching E&M, do that. It's a fun thing, okay? But and then of course the way how I would normally keep, I could actually incorporate this is that in my mean field decoupling, I would enter this layer dependent Coulomb interaction to both the Hartree and the Fogg part, okay? For both of those, this is always going to give you to a quantitative suppression for some momenta when you are talking about charges which are not perfectly layer polarized and don't sit on the same layer. But the most impactful role of this, which is going to matter us, is if I were to decouple the Q0 component corresponding to the Hartree term across the layers, and that is what I'm talking about, the H-perp. And then such an H-perp will have a form. Will have a form of essentially some electrostatic potential, which I must determine self-consistently. And I can map it back, and I can show that this is the case, that actually the difference between the electrostatic potentials on each layer is just the same geometry of parallel sheets of charges, okay? And in here I have chosen the particular description that I am referring to the back gate, okay? But of course the back gate plus the top gate are equal to the negative of the total charge in the system, okay? and you can actually reformulate this that if I wanted to pull out what is called the constant term, then this is the way how normally the electrostatic potential difference would enter, but then you have this correction here, which is coming from redistribution of their charges, and strictly this becomes layer charge independent if all of the charges are the same, okay? All right. So now if you would like to read a bit more about this process, then this is something that I keep writing in appendices of my papers, so none of these papers are necessarily about this, but if you would like to read that, then it's there. Also, I would like to say that there's a very nice discussion in the Moore FCI 3 paper from Andre's group on this, and I would say it's my theory that for every topic in graphene field there exists a Paco article that has touched on it. So indeed there are earlier papers, okay, but none that focus on the emergence on the single gate tracking features. Okay, so now if I solve this problem self-consistently, okay, and for now let me just focus on the electrostatic Hartree physics between the layers, because that's the one that I can tell also something analytically. What I find is that for the negative feelings, indeed the zero chemical potential, which is the surface state location, now is pinned to my back gate, or sorry, to my top gate contour, and this is the surface state which is localized on the bottom device. The top gate is the one on the top, which means that this surface state is independent of the charges on my top gate. Okay. Now for the positive dopings, I get a feature which doesn't seem to care that much about where are the gates, okay? But at the same time, I am not yet worried about this, because I know that that feature comes out of symmetry breaking, so it is not accounted in my model. And for now, if I were to compare how the electrostatic potentials look like, you are going to notice that, of course, they are different, and there's a potential drop which is inhomogeneous across the layers. Okay, and now the other thing which I would like to show you, so for now let me focus just on this, is that is not an artifact of fine-tuning dielectric constant. It's that if I vary the dielectric constant in my system over a wide range of charges, then this electrostatic mechanism is actually guaranteed to pin it to the one fixed gate orientation. Unlike if I were to take the problem and just enter the fixed layer potential. Okay, good. So this is the outcome of numerical simulation. So I would like to now develop some analytic intuition for what actually I am seeing. So if I ask how does the energetic location in the spectrum of the band of my surface state, how actually does it evolve with the gates? So I can write the chain rule. So this is what I would call a compressibility with respect to one of the gates. Okay. And here I am introducing this element called WL, which is just telling me how much of a particular state is localized on a layer L at the particular Fermi level. Okay. And so the physical intuition for this is that if I have some state K, then it will have some unequal distribution of these WLs, but they all must sum to 1 because of probability density conservation. Okay, so now if I do some extreme simplifying, and by that I am saying that let me assume all of my K states have the same distribution of the WLs. Okay, just for simplicity of this analysis, then I would find that the form of these equations is actually fairly simple, and it has 3 generic terms. You have term which is inversely proportional to 1 over rho, which is the compressibility. Then you have a term which is proportional to delta D, which is symmetric between the 2 gates. So that is just capturing the physics that if I redistribute some charge on one layer, it can locally change my chemical potential, and that's why it's symmetric. It's a form of a self-interaction. And then the last term, which is asymmetric between these equations, and as a consequence of the gauge that I have chosen. If I were to be working with a different gauge, then I shouldn't be looking at d partial mu. I should be looking at the partial mu of mu minus u1, which is the potential on the layer 1. Okay, so which is dependent on the distance with respect to the back gate. So I have reduced my problem to 3 characteristic quantities. There's a quantity corresponding to the density of cetates. There's a quantity which is describing my average location of where the cetate is sitting, and then there's a second quantity which is capturing how much that cetate is delocalized across the layers. Okay, and then I ask, yes, yes. Yes, which is similar to the experimental setup. Yeah. Yes, the N, B, and T are set by the voltages on the back gate and top gate. They are the amount of charges that you have put on the back gate and the top gate, so they are connected to the voltages for the gate capacitances. Yes. So now, if I am asking what controls a constant chemical potential trajectory, or put it differently, what allows me to pin my surface cetate to the Fermi level as I am varying the one of the gap gates, one of the gates, then I can find that if I insist on this fixed location, then my equal or my constant mu trajectories, they are going to necessarily follow this linear relation for infinitesimal changes between the gate charges, which is parameterized by this number alpha. And if I think about it in the plane not of nu versus d, but in the plane top charge and back gate charge, then if my alpha is positive, that means that I am counted away from the fixed back gate line. Okay, if I have alpha equal to 0, then that means I have a perfect gate tracking. Right, in here case I am perfectly tracking the top gate, and if my alpha is negative in this case, then we will go like this. So the physical picture, as you are going to see, is that if I have a surface cetate which is localized on this layer, and I have a rest of the cetates which are somewhere in the bulk, or maybe not as localized in the top layer, then the rest of the cetates can screen the top gate. Okay. So now this alpha can be expressed in the parameters of my model, and that's a very nice expression that I can now now I can analyze in this form, that I have two axes. Okay, the y-axis, it is a way to capture how to what extent I can think of the system as delocalized sheets, meaning that if my charges were polarized to one layer, if my charges have very low spread, then that means delta D is 0, and then I am pushing along this y-axis. Okay, and on the x-axis I have this term which is characterizing the competition of the electrostatic Coulomb energy along the perpendicular direction to the kinetic energy. Okay, and you see that and necessarily this quantity is always bigger than 1. So what I would like to show you is that the key condition when I'm going through alpha 0 region, which is this one, this is perfect gate tracking. It occurs when this condition is satisfied. Okay, and this condition when alpha is negative, which is not perfectly gate tracking, if you wish, it's over screening, it's actually corresponding to the negative alpha. And it's an experimental fact that to a large extent you don't see this ever. Okay, that's a you know, that's just something that you noticed. And the way how perhaps you can interpret why this happens is that if I rearrange this condition, I find that, you know, I can perhaps put it in the form of a Cytoner criterion, which is controlled by the perpendicular dielectric constant. Okay, now if I think about it on the, you know, very pictorial level, the dielectric constant that you actually need to include to account for the screening from remote bands, if you're doing a Hartree-Fock calculation, is going to be bigger than that. So what I am arguing is that by this condition alone, you are anticipating that your system would actually want to undergo symmetry breaking, and it does not want to be in this over screened regime. Okay, so let me do a sanity check for graphite. My separation between the two charges on the layers goes to infinity. My E delta D is very tiny. My states are localized to a particular layer. So then you can show that your alpha is approaching 0 from the positive side. So actually, I would not expect to see in graphite symmetry breaking transition, and I would be rather seeing this perfectly gate tracking lines. Okay, but when you have a finite number of layers, then it is interesting because you can explore the competition between the different terms. So this is in fact what I am showing in a way in this plot. Let me go back. Oh, froze. So on this plot, you see that I have put two lines, and one is for a nu, which is -0, which is Hall doping. So that one is positive alpha. So I am anticipating it to perfectly gate track. There's no need for symmetry breaking. If I look at the positive doping with no symmetry breaking, then I'm in the negative alpha region. And then upon symmetry breaking, because I reduce density of states, I will go back to the positive alpha region. And that is my conjecture for what is happening here, that if I do just calculation without symmetry breaking for the positive dopings, I will not get this negative alpha region. Okay, and my laser is overheating, so that's why it's not pointing. Okay, good. So let me do a minimal model of the symmetry breaking. Similar results would hold if you faithfully account for the Fock term. So what you find is that upon allowing for the symmetry breaking, the gate boundaries. Give me a second. Okay, the gate boundaries seem to match where the symmetry breaking transition occurs. Okay, when I go from a symmetric state to a half metal, and if I plot what's the occupation of the surface state, I will find that it's actually matching the symmetry breaking boundaries. So that part of my picture holds. And actually, interestingly, if I think of this further, that the slope of this boundary is set by the slope of my surface state. So that's the explanation for why the boundaries of the symmetry broken region seem to follow a single gate. In the experiment, I am talking here of this boundary and this boundary. I am not including in my calculation that citate here and here, which would correspond to a quarter method. Okay. And the other question is that the width of this region is controlled by the amount of the Fock term. Okay. All right. So as I said, when I reduce my density of citates, I go back to the alpha positive range, and then I get my gate tracking. Okay. So now I have 10 minutes, which means that I'm timed well. So what I am taking from this analysis is that layer-dependent Coulomb interaction is important, but what I think is more important to ask is how does it manifest in the systems which are more interesting, okay? And the next thing which I would like to ask is whether I can use this phenomenon of single gate tracking to be able to tell you something about the underlying electronic structure. And I think the answer is yes, okay? So if I now look at the rhombohedral 8-layer data, so this is a data from Matt and Joshua, which we recently put on the archive. This is n equals to 8. The system is unaligned to the HBN. And then I am noticing that there are these regions which are marked here in black. For now, you can ignore all of those other features, okay? And across one of such boundaries, if I look at this, if I fix a particular backgate voltage and I adjust vary VT, what I find is that across the zone boundary, my Landau levels, which were previously controlled by the top gate, once you cross through the boundary, become independent of the top gate. Okay, they are parallel. And if I were to do fermiology, I would find that it goes from approximately 0.25, which is a fourfold degenerate single Fermi surface, to something which is it's neither 0.25 nor 0.5, which you could interpret, and that's the way that we think holds, that you have coexisting Fermi surfaces of opposite signs such that they add up to 0.25. Okay, so if I repeat my analysis, but this time I am treating Hartree-Fock faithfully, and I actually don't need to do this parallel plate model, then I would indeed capture the emergence of the boundaries, okay, which are marked here in black. So that's actually also that boundary here, but this is not gate tracking because of the layer polarization. And this is corresponding, if you look at the squares and the dots, to a transition from a situation where I have citates that are a single band, which is polarized to one side only, to a situation where I have coexisting bands which intersect the Fermi surface, but crucially, they are polarized to opposite sides of the device. So that's something that I can learn from this, okay? And that is the interesting part, because this means that the superconductivity, which is bounded by this region, is in a situation that I have distributions of charge that are polarized to opposite side. It's a fairly thick device. It has 8 layers, and the system is superconducting. So there are, yes. That's yes. Well, I think in the 5 layer system, you are not going to necessarily take advantage of this physics, right? Which I will capture later, but I think the 4-layer superconductivity that is happening here, right? And yeah. Yes. I think they have not pushed their device to that particular value. So so far as I understand, they are not seeing any superconductivity here. I am not sure if I'm understanding or hearing your question. Okay, 5 minutes. Okay. So the reason that that actually the layer dependent interaction matters is because if I were to plot density of states at the Fermi level, firstly for a non-interacting model as a function of n and the layer potential, the x external layer potential, then I would generically get the region of coexisting bands. That's just a feature of the model. And then at some point I will have an insulator. Okay. Now, if I were to do a layer independent interaction, so the tangent, then I find that actually this coexisting band region is squished. And there is a physical picture for it, meaning that if I have bands which are polarized to opposite side of the device, I have no gain in Coulomb energy if I choose to occupy two bands that are polarized to opposite sides. It's actually the same cost as if I had all of my Coulomb charges in a single band. So in this particular case, what is actually happening that my system chooses to minimize the energy by actually lowering the kinetic energy and making your band flatter. So the point is that the layer independent interaction, I would say, artificially inflates the region of displacement fields over you would expect to see an isolated flat band. Okay. And now if I add the layer dependent interaction, then I further increase this region as well as I recover these regions of straight lines, which give rise to the gate tracking. Okay, so now if I want to discuss just a bit summary of this part in more detail, so I am saying that in this region bounded by the band insulator, in this multi-layer rhombohedral graphene system, this region is a coexisting band region where you have charges polarized to opposite sides, okay? And there I think it's a qualitative statement, or I'm conjecturing it, that you must include this physics in any model. So, okay? Now at the large D, which is over here, you know, that is the part that is difficult, okay, and I would just like to acknowledge that to my knowledge from all of the groups that have analyzed the high D field and region over here, where you see superconductivity, or you see the FCI when it's aligned with the HBN. Andre's group is incorporating this physics of a layer dependent interaction. Okay, now these coexisting bands are actually important for superconductivity, and that's not a statement from a theory, that's a statement from experiment. So Matt actually has a paper, it's in the same paper, he has a data which is 7 layers aligned with HBN, and then he sees pronounced superconductivity only for a particular sign of a D field, and that is corresponding to a conduction band which is polarized away from the Moiré interface, and we can capture that in a mean field too. So here my Moiré interface is at 0, so everything which is blue is polarized towards Moiré interface, and you find that if my conduction band is polarized towards Moiré interface, then the electrostatics suggests that I would like to have an isolated band, but if it's polarized away, then the bands prefer to coexist. I have a minute. And now the superconductivity is just a comment, but Andrei has left, so okay, which I just want to say that this is a boundary between unpolarized and a polarized state, and the superconductivity exists on the unpolarized side. And just as a theory, as a fun theory problem, I think it's interesting to ask what is how does this reservoir of additional electron charges impact the superconductivity. So the naive picture that I have is, for example, from this prediction from Little, that you can have a synthetic Coulomb induced superconductivity, or I can also think of it that this reservoir of valence band charges, it's decreasing my Coulomb repulsion, my mu star, consequently increasing TC, but that's just a conjecture to be checked. Okay, so with that, I just wanted to go through summary, so I hope I have convinced you that layer-dependent interaction is important, that it can give rise to qualitatively observable phenomena, not just numbers, okay? And I think that in rhombohedral system, it matters for superconductivity. So if you ask me what's the different way of naming my talk, I would say it's a Hartree correction, not the hero that we deserve, but the hero that we need. Okay. And with that, I wanted to show the two papers one more time, and thank you for your attention.
Questions?
Thanks for the talk. In a way, you're including quantum corrections to the capacitance of the internal layers. But
yes.
What about the metallic gates? Because sometimes they are graphite or even bilayer graphene.
Yes. So I agree with you. So then actually my calculation shouldn't be set up as a charge on a back gate, charge on a top gate. I should set it up as a voltage on a back gate, voltage on a top gate, and then repeat this calculation. Okay. That I have, yeah.
Questions?
Yes.
Andrei.
So you agree that, so let's say if people would do DFT with gates, these effects would already be in the DFT, right?
Yes. But I think you would need to do a DFT at every single NB and NT combination, right?
I see, right, yes. Right. Like a slab with...
yeah, I think so, but I have... Yeah.
And the other question is, this regime you're talking is exactly the regime that Nurit, right, was also talking about yesterday, at least in the whole band, right? That's the similar density regime, right? Or 2 days ago.
Yes. So as a good guide, if it's in between the band insulators, then yes, this is the coexisting band version. Yes.
Thank you.
More questions? Okay, Cyprian, I have a question. So in the model, so you have interlayer interactions, and you don't have intralayer?
So in this, so in a rhombohedral graphene system, the charge distribution is uniform, so I do not have an intralayer Hartree correction. I actually do have the fog, so that's always included, but in the Mu and the Mu systems, you do have the in-plane Hartree correction, like for example, Paco has shown from TTBG onwards, yes. So it's just a question whether it's Mu or not Mu that you have in-plane Hartree.
Okay.
Actually, I would like to understand the situation with Moray a little bit better. I don't know if you actually have a calculation with Moray.
Yes. So
let's say we take the 5-layer problem that a lot of people are thinking about. Yes. So and then you put the charges away from the Moray. Yes. If I understood correctly, what you're saying that we should be very careful about what happens to the leftover charge? In other words, the potential is not distributed uniformly.
Yes.
One should be worried about the charge that's close to the moire. There's not much charge left there, but there's still some charge left. And in the case of moire, next to the HBN, is it going to produce some non-uniform charge distribution? And what is that going to do on the away layer? Is that effect included?
Yes. So this is included here. Yeah. So
I see.
So this is this is 7 layers on HBN, and we actually treat the coupling to HBN like Andre does, and then. So there is some in-plane distribution too. If that's but I actually maybe you could ask me later, and then I can check. Okay.
Does it change churn numbers?
Okay. I can comment on a different system that actually we have analyzed a lot, which is the 2 AB plus twist ABC system. So what you generically see that the churn numbers are the same, but depending if you include or don't include the layer dependent interaction, the phase boundaries change or sometimes decrease a lot. So that I think is a matter of details, but in that system 2 plus 3, I haven't seen a region disappear completely. But also it's important to say that the churn number physics is important in this large D field. And in the large D field, I anticipate this to not be important physics. Yeah.
Thank you.
So, sorry, just to get back to this, to Oscar's question. So if I add moire, there's this effect of Coulomb dependent that you,
yes.
but do you agree there's also an effect from the valence bands?
Yes.
So that Hartree is also included.
That's right. So okay. Here we include 6 and 6 on the top and bottom. Yes. Excellent. But I absolutely agree that actually in the epenta layer, right? If it matters if I include the valence band or not. If I don't include, I will generically get bands which are very flat. If I include them, then the bands are no longer as flat as the first generation theory would suggest.
Excellent, thank you.
More questions? Okay, if not, let's thank Cyprian again. So our next talk is online.